Now that we are explored the benefits of using threads, let's take a closer look at user threads and kernel threads. So user threads, user-level threads, are managed entirely by user-level libraries or applications without kernel-level support. Okay, so these threads are created, scheduled, and synchronized by the application itself or a user-level thread library entirely in user space. User-level threads can function across different operating systems with compatible thread libraries. These libraries can contain code for creating and destroying threads, passing messages and data between them, or scheduling thread execution, or maybe saving and restoring thread contexts. Okay, and developers can create specialized scheduling algorithms, and we as an application developer can easily control user-level threads. If we look at the characteristic of user threads, we see that user threads are lightweight because they don't require kernel resources for management. They are created and controlled by the application itself, and which is make them faster to create and switch between. Okay, since user threads are managed at the user level, context switching between user threads is typically faster than kernel threads, and switching user level threads without involving the operating system kernel reduces overhead. The number of user threads an application can create is limited by the application itself. If the application creates too many threads, it might impact performance due to resource constraints. Okay. Lastly, user threads do not benefit from multi-threading capabilities of underlying hardware, such as multiple processor cores, since the kernel is not involved in their management. The operating system kernel is unaware of the existence of user threads. Okay, so we can say that in user-level threads, the kernel's involvement is limited. They are controlled entirely at the user level, meaning the kernel isn't aware of specific thread actions. It only observes the entire process and its overall status. Okay, so when a thread in a user-level thread system makes a system call, the whole process, along with all its threads, is halted. This implies that if one thread initiates a blocking system call, the entire process, including all threads, stops. However, from the perspective of the thread library managing this user-level threads, the thread is still considered running, even if it's blocked at the kernel level. Okay, so in a sense, user-level threads operate within the user space, and while system calls can pause the entire process, the thread library maintains its own understanding of thread states. Let's look at the kernel level threads. They are managed and scheduled by the operating system kernel, and each kernel thread is an independent unit that the operating system schedules on a processor core. Okay, so the kernel provides direct support for creating, scheduling, and managing these threads. Let's look at the characteristic of kernel threads. They are relatively heavier in terms of resources as compared to user threads. They have their own kernel level data structures, and they are managed by the operating system as a process. Also, kernel threads consume kernel resources, making them suitable for tasks that require direct interaction with hardware or operating system services. Kernel threads can fully utilize multi-threading hardware capabilities, such as parallel execution on multiple CPU cores, leading to efficient multitasking in multi-threaded applications. And they are managed by the operating system, which allows them for efficient utilization of system resources and balanced workload distribution. As an alternative, in hybrid approaches, thread creation occurs within the user space of the program. The bulk of scheduling and synchronization task is handled in the user space, as well as minimizing kernel involvement and improving performance. Programmers have the flexibility to adjust the number of kernel level threads according to the specific requirements of their applications. This approach allows for the combination of the advantages offered by user-level threads and kernel-level threads. An example of this approach can be seen in Solaris prior to version 9, where this strategy was implemented effectively. To sum up, user threads are managed at the user level, provide us flexibility, but it is limited by application we designed, while kernel threads are managed by the operating system, offering direct hardware access and efficient resource utilization. The choice between them depends on the specific requirements of the application. So in multithreading, we saw that threads can be supported either at the user level or by the kernel level of the operating system. The relationship between user threads and kernel threads can be established using different models. Okay, many-to-one, one-to-one, many-to-many, and two-level model. Let's start with many-to-one model. In this model, many user-level threads are mapped to one kernel thread. Okay. Thread management is handled by the thread library in user space. However, if a thread makes a blocking system call, the entire process will block. Additionally, only one thread can access the kernel at a time. This prevents parallel execution on multi-core systems. This model is not widely used due to its limitations. Yeah. So on one-to-one model, each user thread is mapped to a corresponding kernel thread in this model. It allows more concurrency than the many-to-one model because when a thread makes a blocking system call, another thread can continue its execution. Multiple threads can run in parallel on multiprocessors. However, creating a user thread requires creating a kernel thread, which can introduce overhead, okay? So most modern operating systems, such as Linux and Windows, implement this model. In many-to-many model, many user-level threads are multiplexed to a smaller or equal number of kernel threads. The number of kernel threads can vary based on the application's requirements or the machine's capabilities. Unlike the many-to-one model, this approach provides true concurrency, allowing developers to create as many user threads as needed. When a thread makes a blocking system call, the kernel can schedule another thread for execution, okay? And in the last model, it's actually a variation of many-to-many model. This variation multiplexes many user-level threads to a smaller number of kernel threads. Additionally, it allows a user-level thread to be bound to a specific kernel thread. And this model provides flexibility and concurrency, allowing developers to create numerous user threads while ensuring efficient execution on multiprocessor systems. So these models determine how user threads interact with kernel threads and influencing the concurrency, responsiveness, and efficiency of multi-threaded applications. Different operating systems may employ specific models based on their design and performance considerations.